Hello guys, I'm Lauren Smith. I'm studying a degree in theoretical physics and I'll be bringing you through to 2020's higher level question 6 today. It is a question all about mechanics, in particular force, constant acceleration and the kinematic equations. So let's get started. Okay, so here's the first look at our question 6, and just to point out a little bit of a disclaimer, my overall analysis of this question, and indeed the solution as well, is that it is a mechanics question like no other year, and this is because 2020 was an extremely special year in which to sit the Leaving Cert. A lot of accommodations were made, a lot of so-called easy marks were given in various parts of the question and indeed throughout this paper. So this mechanics question isn't on the same level of difficulty as, say, other mechanics questions from other years, so bear that in mind. You might not get as easy a question in your exam as this question. So without further ado, I am going to look at the first 3 parts of this question to get us started. And the first part of this question is to just state Newton's laws of motion. We just have to state them. We don't have to explain them. Just state them, give a simple definition, and that is all. Again, this question here shows us how nicely the marks were awarded throughout this question. You were given 12 marks for this part of the question. Let me tell you, it won't be as nice in other years. If we were looking at, say, another exam year to state Newton's laws of motion, normally only 6 marks would be given for this type of question. So just bear that in mind, but I'll still go through how the marks were given out throughout this part of the question. Okay, so starting off, we are going to be looking at Newton's first law. 4 marks are awarded for the first law. The first 2 marks are for stating that every body will remain in a state of rest, or you could say that every body will remain travelling with a constant velocity. Either one of these statements will get you 2 marks. Your other 2 marks will come from stating that unless this body is acted upon by an external force. Given 4 out of 4 for this first law. So now moving on to the second law, you're going to get your first 2 marks for stating that the rate of change of a body's momentum, 2 marks, and your other 2 marks are coming from the fact that this rate of change of a body's momentum is directly proportional to the force, giving you 4 out of 4 for this second law. And finally, you're going to get 4 marks for the third law. Your first 2 marks will come from the phrase, if a body A exerts a force on a body B. And your other 2 marks will come from explaining the second part of the law, which states that body B exerts an equal but opposite force on body A. Giving you 4 out of 4 for this third law and 12 out of 12 in total for part 1. Okay, so in part 2, we're asked to show that F is equal to ma is a special case of Newton's second law. And we're going to start off this derivation with the definition or the relation between force and momentum. And of course we know that the force, or this force in question, is directly proportional to the change in momentum, which is just the mass times the velocity, over the change in time. This little triangle here denotes in mathematical terms the change of. Stating this will get you 2 marks. Now, since they are proportional to one another, this means that they only differ by a constant factor, which means that you can write the force like this, where k is just some constant factor here. Now, I was able to express the numerator like so, because we only need to have delta in front of the velocity, since delta means the change of, and we're only going to have a change in velocity, and we assume that there's going to be no change in mass. It's going to remain a constant. So that's how I did that little manipulation there. Now, this line here will get you another 2 marks. However, we know that the definition of acceleration is the rate of change of velocity with respect to time, i.e. a, acceleration, the same variable we see up here in the question, is equal to delta v over delta t, i.e. the change in velocity over the change in time, and therefore we can write our second law as F is equal to k times m times a, where a is the acceleration. If you write this line down correctly, you'll get another 2 marks, giving us 6 in total. However, for the final 2 marks, we need to state that from the definition of the Newton, which is the unit of force, K is equal to 1. This constant factor is equal to 1, and therefore F is equal to ma. So this statement will get you your final 2 marks, giving you 8 out of 8 for this derivation. In part 3, we are asked to describe an experiment to find the resultant of 2 coplanar vectors. With any description of any experiment in physics, try and structure your answer as drawing an apparatus, explaining the method, and then what are your observations. They're the 3 key parts, and normally the marking scheme is sectioned out into these 3 parts. For example, in this question, you'll get 3 marks for your apparatus, 3 marks for your method, and 3 marks for your observation. What does it mean by coplanar vectors? Coplanar vectors just mean that the vectors are in the same plane, like in a 2D plane or a Cartesian coordinate plane like you'd see in your mathematics class. Okay, so with that in mind, here is my apparatus. And if you were to write this down in the exam, you would get 3 marks. The whole idea behind this experiment is that if we have 3 forces, which are keeping a particle at rest, the resultant of any 2 of them is equal in magnitude but opposite in direction to the third force. And this is keeping in mind Newton's third law, in which every action has an equal opposite reaction, or that's basically a summation of the third law which we stated earlier. Key parts of this apparatus is, of course, the knot in this thread here is at rest, and we've got pieces of thread, and at the end of the pieces of thread we've got our Newton balances, which are spring balances graduated in Newtons, and they measure the force of tension, which is the force in question, which is holding the knot in place. I've also drawn in my vectors here and the direction they're going in, and as you can see here from my little diagram to the right, you won't get any extra marks for this, but it's just for your benefit. You can clearly see by the parallelogram law that the magnitude of force 1 and force 2, which is just this purple line here, is equal in magnitude to the third force here, but it's opposite in direction. And that's the idea behind the experiment. Now moving on to method, all we have to say here is that we need to set up the equipment as shown above, and we have to adjust the size and direction of the 3 forces until the knot in the thread remains at rest, because that's again the whole idea behind the experiment. You'll get 3 marks for this method here. Moving on to observations, all we have to state is that the magnitude of the resultant of the 2 forces, F1 and F2, or any of 2 forces in your diagram, just make sure you explain it, is the reading on the third balance, i.e. for F3. The direction of the resultant is in the opposite direction to F3, or the third force. These observations will get you 3 marks, and when you're always describing your observations for, say, vectors, explain your observations for the magnitude of the vector and the direction, because they are the 2 most important qualities of vectors. This concludes the description of our experiment, giving us 9 out of 9. Okay, so we're now looking at the next section of this question, and we are told that a cricket player moves her hands away from the motion of the ball as she catches it. With this information, let's go ahead and look at part 4. In part 4, we're asked to explain, using Newton's laws of motion, why she moves her hands away from the motion of the ball. And it can be answered as follows. The force is inversely proportional to the time interval, and i.e. the longer the time interval, the smaller the force. So that's a verbal definition, and it can be equally as expressed in this mathematical relation here. When the ball flies through the air and it goes into her hands will experience a force. To minimize the force, which is what we want because we want to avoid, say, discomfort or pain, which leads to her actually not catching the ball, we need to lengthen the time frame. Since we know through Newton's second law that the force is inversely proportional to the time interval. So longer the time, smaller the force. If you give either this definition here or this definition up here, you'll get your 3 marks, no problem. Bringing us back to the original question again, we're given information which we will need to consider when we're answering parts 5, 6 and 7. We are told that the cricket player throws a ball upwards with initial velocity of 28 meters per second and the direction is at 45 degrees to the horizontal. This direction is important to note since velocity is itself a vector and we need to consider the magnitude of the vector, which is 28 meters per second, and the direction, which we are given the angular direction in this case. We're also told that her hand was 1.6 meters above the ground. We're told that a short time later, the ball was caught by another player, and when it was caught, the ball was again at a height of 1.6 meters. So if we were looking at vertical displacement, it started and ended at the same spot. So overall, the net vertical displacement would be null if we are looking at the end point here. Okay, so we better move on to actually answering parts 5, 6 and 7. But before dipping into any of these parts, I want to draw your attention to page 50 of the Formula Tables book. This page is going to be very important since we need the formulas for linear motion with constant acceleration, because that's what we're working with here. The constant acceleration in this question is obviously going to be the acceleration due to gravity, which is constant, and it's given at the end of the question. In particular today, we are going to be looking at the first 3 formulae. For part 5, we are asked to calculate how long the ball was in the air. This also is in reference to what's called the time of flight, which is the time the ball spends in motion, or the time taken to travel the horizontal range. Now, you know me, if you've watched my videos before, I always love drawing diagrams for mechanics questions because I feel like they're very, very beneficial, and I would encourage you to draw as many diagrams or pictures to try and visualize what's going on in your exam, because you might be able to spot different things which you wouldn't be able to do without them. So, how do we draw a diagram for this question? Well, you can simply draw something like this, and you can kind of use this graph as, and you can kind of use this diagram as a template for all similar mechanics questions of this type. Bear in mind, it is helpful, this diagram, when we're answering not only just part 5, but also part 6 and part 7. Since velocity, displacement, and acceleration are all vectors, which I will be denoting as v, s, and a respectively, it is useful to split them up into their components, i.e. their vertical and their horizontal components. Any vector you see with a subscript of x, it's going to be that vector component in the horizontal direction. If you see a vector or a letter with a subscript of y, you know that that's the vertical component of that vector I'm talking about. For example, let's look at the acceleration vectors, which I have to the left. We know that for a mechanics problem of this type, the horizontal acceleration is indeed 0, and the vertical acceleration is minus g, or minus the acceleration due to gravity. Since I will be denoting all of my vectors, vertical vectors pointing up as positive, and I'm going to associate my downward direction vectors with a minus sign. Okay? Associate a sign with a direction whenever you're dealing with vectors here. Next, moving on to my displacement vectors. The range of this ball is from the starting point to this ending point over here. When I talk about range, I'm talking about horizontal range here for s of x. And the maximum height above the ground, I've denoted here, is s of y, which extends from this point here to this point here. It's the vertical displacement, plus this 1.6 meters. That's the maximum height above the ground. Okay, so from the top of s of y down to the very ground, that's the maximum height. Moving on to velocity vectors, we know that at this maximum height point here, that the vertical velocity component is 0, because it's not traveling upward anymore since it's at its maximum height. After this point, it's just going to be traveling downward. We were told at the very start of the question that its initial velocity magnitude was 28 meters per second, and it was in a direction of 45 degrees to the horizontal, which I've drawn here in a little right-angled triangle. And we know that the horizontal and the vertical components are just such sides of this triangle here. Okay, so without further ado, let's move on to part 5. And I'm going to answer it using the formula s is equal to ut plus a half at squared. Even just putting down this formula will get you your 3 marks. Since we are looking at the time of flight, we need to find out what t is. By the way, this is just a note. Because we are looking at vectors, you must, when you're using any of these formulas, break up the vectors into their separate components and only use, say, either one component over the other with these vectors when you're putting them into the formula. For instance, here, when I'm plugging in values into this formula, I'm only going to use values from the vertical components of our vectors. You can either do this with the horizontal components of the vectors, but it can either be one or the other, not a mix of both. I just want to put that out there. The reason why I'm going to be using these vertical components here is that it's the easiest way forward, and we know the most amount of information. Since at the end point, we know that this overall vertical displacement is 0 because it starts and ends vertically at the same point. We know the vertical component of the acceleration is just minus g, which is just minus 9.8 meters per second per second. That's the acceleration. And we also know u, or we can figure that out from our triangle, which I've drawn here. And we know that the vertical component of the initial velocity is just the hypotenuse of the triangle multiplied by the sine of the direction angle here, using our trig identities. So what does that make u sub y? Let's put that into our calculator, making sure that the calculator is in degrees and not radians. Otherwise your answer will be wrong. Plugging this in, we get 14 times the square root of 2 meters per second as our velocity component in the vertical direction. Now we have all of the information needed to solve this question. We're solving for t. I've plugged in all of our values here. I've taken out t as a common factor in both of the terms, and this either means that t can equal 0 or this bracket in here can equal 0, and they are both answers since this is a quadratic formula. T is equal to 0 makes a reference to that when the vertical displacement is 0, this is also at the starting point, but we're looking for what it is at the end point, or to find out how much time has elapsed. So therefore, we can let this bracket equal to 0 and we get and we can let this equal to 0 as we done over there. And I'm going to manipulate this further. I'm just putting all of these steps in to basically encourage you in your exam scripts to always put down every single step to the answer as possible. You don't know where you can pick out marks from. Finally, we get that t is equal to 14 times the square root of 2 over 4.9, but we're going to have to put this in decimal form to get any marks from it. So we've kept this up on screen, this answer here, for the vertical component of the velocity. And that's going to be stored as an answer, so we don't need to write that out again. And that's going to be over 4.9. Hitting that equals sign, we get that the time elapsed is roughly 4.04 seconds. And our final answer gets 3 marks, giving us 6 out of 6. Now you can also use the formula v is equal to u plus at and use a similar method as I did there, and you'll get the same breakdown of marks. 3 marks for the formula, 3 marks for the answer. We were also asked in part 6 to calculate the horizontal distance travelled by the ball. And this basically refers to S sub x, the horizontal displacement of the ball, as I've labelled in the diagram we showed in part 5. With this in mind, I'm going to be using the same s equal to ut plus a half at squared formula. Putting this down gets us 3 marks. But I'm going to plug in all of the vector components which are in the x direction, the horizontal direction, since we are indeed looking for s of x. It makes the most sense. Well, we already know the elapsed time that was figured out in part 5. We already know the horizontal acceleration, that's 0. To find out what u of x is, we again draw our little triangle for our vector. We are told that the initial velocity is 28 meters per second, and it's in a direction of 45 degrees to the horizontal. So we are looking to calculate the adjacent of this triangle here, which is just going to be the hypotenuse, which is 28, times the cosine of the angle, which is 45. Putting this all into our calculator, we are still going to get out 14 times the square root of 2. It's the same numerical answer as the vertical component of the velocity, the initial velocity. And this is because we have a 45-degree angle, and that's just the nature of these triangles here. So we know all of the variables. Now we can just solve to find s of x. So I've just subbed everything in, and this leads to a very nice answer, because we know a of x is equal to 0, and therefore this whole term equals to 0 as well, leaving us just with 14 times the square root of 2 times 4.04, which is the time of flight. Pulling this up in the calculator, we still have our answer there from earlier, which is our horizontal component of the initial velocity. We're going to multiply that by 4.04, and therefore we get this as our range. And it's roughly going to be 80 meters, rounding to the nearest whole number, giving us our final 3 marks. Now in part 7, we need to calculate the maximum height above the ground reached by the ball. So this is above the ground. As I explained in the diagram in part 5, this means that it's not only the maximum height from the point at which the ball is thrown to where it lands, but also we need to include that 1.6 meters, because the ball is originally, when it's in the hand of the cricket player, at a height of 1.6 meters above the ground before it starts to move at all. So we're going to have to take this into account. Now you can either use the same formula as we've been using throughout this question. Here, s is equal to u2 plus a half at squared, or you can use the formula v squared is equal to u squared plus 2as. Just for a bit of variety, I'm going to use the right equation here. And by plugging any of these formulae down, you're going to get 3 marks. So always, always, always put your formula down. You're automatically going to get half the marks for this question. We're looking for maximum height, and in doing so, we need to find what s sub y is, the vertical component of the displacement vector. We already know the time that the ball has travelled in, which is 4.04 seconds. We already know the acceleration in the vertical direction, that's minus 9.8 meters per second. We also know the vertical component of the initial velocity, that's 14 times the square root of 2 meters per second. So we can use this formula up here to find what s of y is. Since we also know that when it's at its maximum height above the ground, the vertical velocity is 0. Again, breaking up this equation up here into its different components, we're just going to use all of the components in the y direction. But since v sub y is 0, we can already automatically replace that with 0, leading us to calculate what this is. Plugging in all of our values here and manipulating it as follows. This minus 19.6 comes from the fact that we have 2 times minus 9.8, which is the acceleration due to gravity in the y direction. And therefore we get this for s of y. So plugging this into our calculator, we get 14 times root 2 all squared. Remember to use brackets, especially when you're dealing with square roots, because it's easy to make a calculator error. And that's all over 19.6. Hit that equal sign and you just get 20 meters out. However, they were looking for the total maximum height above the ground, not above the cricket hand, above the ground. So max height is equal to 20 meters plus 1.6 meters, which is just equal to 21.6 meters. Not forgetting our units, giving us our final 3 marks. And finally, in part 8, we are asked to draw a diagram to show the velocity v, acceleration a, and forces f on the ball when it's at its maximum height. And we are to use the letters v, a, and f to label the vectors. The diagram I have drawn is as follows. It follows directly from the diagram that I've drawn in part 5 as well. Just a little bit of more of a close-up, and that orange circle there in the middle just represents the ball. The velocity vector v is horizontal. There is no vertical component of the velocity, since at maximum height we noticed that v sub y is equal to 0, because there's only horizontal velocity left since it's at its maximum height. And for realizing this with the correct direction and everything like that, you'll get your first 2 marks. Now, we never have horizontal acceleration, only downward acceleration. since the ball is getting pulled downward by gravity. So our acceleration vector is going to be in the downward direction. Correctly expressing this gives us our next 2 marks. Since acceleration is only in the vertical direction, therefore the force on the ball is only in the vertical direction and in the same direction as that acceleration due to Newton's second law, because it follows that force and acceleration are directly proportional to one another. Realising this for the force gets us another 2 marks, giving us 6 out of 6. I just want to note out that all vectors are acting through the centre of mass of the ball, which is just noted by this little green circle here in the centre of the disc I've drawn. And that's our question finished.